How many people now? Okay, good. All right, so let's get started. So today we are going to talk about chapter 9. So chapter 9, we're gonna cover 3 sections. So first, we're gonna do section 9.1, approximating functions with polynomials. So this is the one that's similar to what I told you on the last class. We're trying to approximate a complicated function by using polynomials. And then we're gonna shift to section 9.3 later, so Taylor series. And this is because Taylor series is the extension of Taylor polynomial, so we just move section 9.3 to learn first, and then the last one gonna be section 9.2, which is the power series. This is a special form of series that have so many properties. Okay, let's start by section 9.1. So we are trying to make the approximation of function by using polynomial. So the idea is the same as last time I told you. So this is the case that we feel like we cannot compute function easily. So why don't we just approximate it by polynomial? Something like if you see the function cube root of x to the fourth power minus 1. This one is hard to compute. If you plug in like 1.02 or any number that is hard to compute here. So when you plug in it and then, you know, like with the cube root, you don't have the formula to do it. So we're trying to approximate it by using polynomial. So the polynomial is going to be the function that you can compute it easily. So the person who proposed the idea is Taylor, as I told you last time, that he proposed that why don't we use the Taylor polynomial to do it. So this is the formula for the Taylor polynomial. So the component of the Taylor polynomial gonna have, first you're gonna have the degree. So let f be the function with the f double prime up to f degree n defined at x equal to a, which means when you do the Taylor polynomial, you have to differentiate until the order n. And then now we're gonna say that the n order polynomial, Taylor polynomial for f centered at a is Pnx here. Basically what you're trying to do is you need to compute Pnx. This is the form of the Taylor polynomial. So the way you memorize it, you're gonna do remember that you're gonna do up to order n, so you have to differentiate n times. You see that they're gonna have differentiate 0 times, 1 time, 2 time, up to n time, and then you plug in the value a here, and then after that you do the x minus a square up to x minus a to the n. They're gonna keep having x minus a with you, and then the coefficients gonna be 1 factorial. I mean the gonna be 1 here, 1 over 2 factorial here, 1 over 3 factorial, the next one up to 1 over n factorial. This is the Taylor polynomial. So as we tried to do it last time, so we have fx equal to e to the x. Let's redo it again. You can differentiate 1 time, 2 times, 3 times. So this one you get the same thing, e to the x, which mean well, remember that we need to, for this question we want to find the Taylor polynomial of degree 3, degree 0, degree 1, degree 2, and degree 3. So because I want the Taylor polynomial up to degree 3, so you're gonna differentiate 3 times, and then each time after you differentiate it, so you plug in at the center here is 0, so you plug in at 0. So you're gonna get e to the 0, which is 1. Now f prime 0, you're gonna get e to the 0 as well, which is 1. This is the same question as we did on Monday, e to the 0, which is 1, and the last one actually it is 1. And then when you combine it for the Taylor polynomial, so you can start by saying the Taylor polynomial of degree, let's say degree 1, for example, degree 0, for example, degree 0, you're gonna get f0, which is 1. the Taylor polynomial of degree 1, it's gonna be f0, and then now you remember the way we memorize it. You're gonna start from f0, and then you add f prime 0, and then times x minus 0. This is the Taylor polynomial of degree 1, which is 1 plus 1 times x. This is 1 plus x. And then for degree 2, it's gonna be the same thing, but you just add the second term 1 over 2 factorial, and then f double prime 0, x minus 0 square, and that is 1 plus x square over 2. And then you keep doing it, so the Taylor polynomial of degree n gonna be 1 plus x square over 2 factorial plus x cubed over 3 factorial plus dot 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 up to x to the n over n factorial. Well, this should be your first example when you learn Taylor polynomial, and this is how we do it. So we're gonna say that you can approximate e to the x by using this one. This is how we do it for the Taylor polynomial, and actually we just did it on Monday. This is the Taylor polynomial formula. Alright, if you know how to do it already, maybe you do the next question. It is the Taylor polynomial of degree 5 for the trigonometric function. I think the Sine function, the next one, yeah. Sounds good with this one? Okay. Alright, next it's gonna be Taylor polynomial for Sine function. Alright, example 2. Can you find the fifth order Taylor polynomial for fx equal to sine x center at 0? Alright, so when you read the question, you can see that I need the fifth order Taylor polynomial, which means you need to differentiate 5 times. Fx equal to sine x, this is the first time. And then differentiate, this is just a function. You differentiate 1 time sine, you get cosine. You get differentiate another time, you get differentiate cosine, you get negative sine, right? And then you differentiate the third time, so you get negative cosine. And then you differentiate one more time, the fourth time, so differentiate cosine, you're gonna get negative sine. But because negative you have in front already, so it's gonna be plus sine. And if you see the pattern, you're gonna see that when you differentiate sine, the cycle equal to 4, right? Because once you hit 4 times, you come back to sine. And then once you hit another 4 times, you're gonna come back to sine. So the cycle gonna be 4 here. Which means when you form the Taylor polynomial, you can guess the pattern from now. And then when you plug in, so you're gonna plug in at 0 because the center is 0. So f0 sine 0 is 0. Here f prime 0, which is cosine 0, this is actually 1. F double prime 0, this is minus sine 0, this is actually 0. And f triple prime 0, this is actually minus cosine 0, which is minus 1. And the fourth derivative is going to be sine 0, which is 0. When you form the Taylor polynomial of degree 5 P5x, what does it look like? So it's gonna be the first term, which is f0, but the first term is 0, so it disappears. And then the second term gonna be f prime 0, which is 1. And then you multiply x minus 0, right? This is the term related to the first degree, the power 1 degree. And then the next term gonna be 0, so it's gonna be disappear. And then the next term gonna be minus 1 times x minus 0 cube. And then the next term gonna be 0, right? And then, we're gonna do to the fifth order, so we're gonna do one more. So f to the fifth order is going to be cos here which mean you when you differentiate one more time, so you're gonna get cos 0, which is 1. So this is actually 1 times x minus 0 to the 5th power. So the Taylor polynomial of degree 5 for psi x, it's going to be x plus x cubed. Oh, I forget 3 factorial, right? And 5 factorial. Okay, this is the Taylor polynomial center at 0. Does it make sense? So this is how you do this Taylor polynomial for the psi function. Observe that for the psi function, if you do f to the m power at 0 for it's gonna be 0 for all even number m. Right? You can see that the pattern is just every time when you differentiate 2 times, 4 times, 6 times, and so on, they are all 0, because when you differentiate it, it's gonna, the cycle gonna give you sine here, sine, negative sine, sine, and then it's gonna come back sine, negative sine, sine, negative sine on the odd, on the even number, which mean that the term related to the even number m, the derivative gonna be 0 when you do the m order derivative, and which mean for the Taylor polynomial for the psi function, you don't have the even power at all. The same thing with the cosine function. If you do the polynomial for the Taylor polynomial for the cosine function, you're gonna see only the even term. You don't have the odd term. So for the cosine function, you're gonna have x squared, x to the 4th power, but you don't have x cubed, x to the 5th power. Sounds good? Oh, okay. Good catch, ครับ This is minus 1. Okay, thank you. Okay, ครับ This is the Taylor polynomial of degree 3 or degree 5. Good. This is why when you learn physics and people in physics say that, okay, we're gonna approximate psi 0.01 by 0.01. They can do it. It's okay, because this one in mathematics we believe that psi x you can be approximate it by x, but this one in physics we use Taylor polynomial of degree 1. Right? This is actually just the Taylor polynomial of degree 1. So when they compute psi 0.01 in physics, they say, oh, it's approximately equal to 0.01. This is acceptable because we claim that it is true by Taylor polynomial of degree 1. But if you want more precision, you can just say, actually psi x can be approximated by x minus x cubed over 3 fact plus x to the 5th power over 5 fact minus x to the 7 over 7 fact plus x to the 9 over 9 fact. You can keep going, but you know, like the more you use, the more precision you have. Right? I mean, if you use the 2 term, 3 term, 4 term, 5 term, it's gonna be more precise when you do the Taylor polynomial. Okay. Alright. That is how to do it with the psi function. So as I told you before that when you use more terms in Taylor polynomial, the approximation get better. Keep in mind that more n mean you have more precision for the Taylor polynomial. We just discussed this one on Monday already. Okay. Alright, now we're gonna do 2 examples pretty quick before we start the Taylor series. Let's approximate log 0.98 by using log x at x equal to 1 and approximate square root 17. Okay, let's do it pretty quick. How about log 0.98? So the question said that, can you find the quadratic approximation to fx equal to log x at x equal to 1? and use it to estimate 0.98. Okay, let's go. So we're gonna start by let function fx to be log x. What we need is we need to find log 0.98. So we're gonna do the Taylor polynomial of degree 2 because quadratic mean you're gonna find Taylor polynomial of degree 2. Which mean this time you're gonna differentiate 2 times. Log x you get 1 over x. This one you get 1 minus x squared. Pretty simple because what you do here, you're gonna just say this is actually f at 1. Everyone observe that you plug in 1 because the center is at 1. This is why you plug in 1. And then you're gonna do log 1. This is 0. And then 1 over 1. This is 1. Minus 1 over 1 square. This is minus 1. So you compute everything so it's ready to plug in. And then now for the Taylor polynomial of degree 2, it's going to be, the formula is going to be f1 plus f prime 1 times x minus 1 and then plus f double prime 1 over 2 factorial x minus 1 square. Once you do it multiple times, you're going to feel like the formula is so easy to memorize because you just can extend to the n order. Power to the n with x minus a and then keep doing factorial in the denominator, so it's gonna be just that one. And then you plug in everything, it's gonna be 0 plus 1 times x minus 1 and then plus minus 1 over 2 x minus 1 square. This is a Taylor polynomial of degree 2 and we're gonna use it to approximate log x, right? So now when you approximate it, log 0.98, it's gonna be 0.98 minus 1 plus negative 1/2 0.98 minus 1 square. Pretty simple because you can follow the formula here. X minus 1 gonna be this. And this one gonna be this one, right? So just plug in and then you're gonna have minus 0.02 and then minus, this is going to be minus 0.02 square over 2 and that is minus 0.02 and then minus 0.0002, right? Because it's gonna be like 0.0004 and then you cut half, so it's gonna be that one. Okay, this is how you approximate log 0.98. Once you know how to do it, this is pretty boring question, the Taylor's polynomial, because if you can differentiate it, you plug in, you're done. Yeah. So 0.98, right? Am I right?
This one is correct. The later one.
This?
Yes, negative 1, 2, so this one.
Negative is here.
Oh, so here, okay.
Yeah, and then this one is already positive. So, yeah.
Sorry,
Good.
Like asleep, sorry.
Okay, so one more question. So, example 4. This is supposed to be the basic question, for the Taylor polynomial. Much easier compared to checking convergent divergent. Use the second order Taylor polynomial to approximate square root 17. This one you can pick it by yourself. You can pick the function by yourself. You can pick the center by yourself because they didn't give you any idea how to do it. But the idea is you need to pick something close to 17 and easy to compute, which we can see that the number that is super close to 17 and you can take square root is 16.
Yes.
So we're trying to do something with 16. right? Which is that is going to be the good approximation for us. So maybe we're gonna do, let fx to be square root, what should we do, x plus 16.
Maybe just x and cannot.
Okay, x, and then what happened next? What you gonna do next?
Differentiate.
Well, let's try to do fx equal to square root x first, and then let's see what problem we're gonna see. If you have fx equal to square root x, you differentiate one time, differentiate two times, you can do it. However, when you plug in f17, you can see the problem now that
Then you use component.
I mean, it's go back to the same problem. So what should we
X
do
minus
here? I just Pokemon Go app just show up. 16 plus 1, right?
So x minus 1 cannot.
I'm trying to think what is the purpose that I put the question here, because I cannot remember what is the purpose that I put this question out here. But to approximate square root 17, you can trying to do, let for example, you can do x plus 1,
So that should
right?
be 15 minutes.
And you plug in 16. Is that better?
Oh, you can use to plug in 16.
And then you, once you plug in
16. Then it becomes 17.
hold on.
x minus 1.
So if like that, you can just put x on minus 1 and you put.
Hey, what is the purpose that I put this question on? 1 second, let me just do the double check with my thing. I'm pretty sure I put this question for a purpose, but let's see. 1 second, but the idea is that I'm pretty sure that the thing is that 17 gonna be close to 16.
Yes, that's right.
So we're trying to plug in some number that when we compute f prime, f double prime, it's gonna be easier to compute. Wait a minute, because I just did the all calculation already, but it's on my computer. Let's try to do it. So slow nah, when you need it. Lecture. Okay, APU10. Hoop. Okay, the thing is that we're gonna do is what I want here is I said that we're gonna use fx equal to square root x, but we're gonna choose center to be 16. So because when we approximate it, so we can so let's go back to the beginning again. So number 17 here, we can see that 17 is close to 16, right? It's just very close to 16. So when we do fx here, we're gonna trying to do the Taylor polynomial around the center 16. So we will find the Taylor polynomial of degree 2 around x equal to 16. So we're gonna start by doing fx equal to square root x. And then when you differentiate one time, so this is actually x to the 1/2 for fx. So it's gonna be 1/2 x to the minus 1/2. And then double time gonna be minus 1/4 x to the minus 3/2, right? Because you just differentiate. Because we pick the center to be 16, so now it is easy to compute. So it's gonna be f16 equal to 16 to the 1/2, which is square root 16, which is actually 4. So it's easy to compute now because you just pick center smartly, not 17. So this type of question, yeah, so basically I put it because sometimes you just need to pick the center to be the number that easy to compute. And then now you do f prime at 16. But you know, on the exam or on the homework, I mean, when you do the problem in the book, they're gonna specify the center for you, so you don't have to be worried. But this is a problem in real life that sometimes you feel like you just need to specify the center by yourself. F prime 16, this is going to be 1/2 16 to the negative 1/2, which is actually 1/2 square root 16. This is 1/8. And then f double prime at 16, this is going to be minus 1/4 16 to the negative 3/2. So it's actually minus 1/4 square root 16. So hard, nah? Minus. Yeah, let's do it this way. So we're gonna just do minus 1/4 first. 16, this is plus, right? Whoop. 16. We're gonna do 16, take square root first, so you get 4. And then you do 4 to the negative 3, which is 1/4 cube. And that is minus 1/64. Okay, now you have it. And then now the Taylor polynomial of degree 2 of the function root x gonna be f16 plus f prime 16. คิดเลขผิดเหรอ oh yeah, it's 256. Yep. Okay. Is that correct now? Because it's 4 to the 4. And then now this is x minus 16 plus f double prime 16 over 2 factorial. So you still have 2 factorial here because this is a form of the Taylor polynomial. Okay. And then now it's going to be 4 plus x minus 16 over 8. And then plus x minus 16 square minus 256 multiplied 2, which is 512. Okay. This is the Taylor polynomial of degree 2 for this function, which means you can approximate square root x by this thing. So what we're gonna do is, if you want square root 17, so it's gonna be 4 plus 17 minus 16 over 8, and then 17 minus 16 square over 512, right? Which you do it, you're gonna get 4 plus 1 over 8 minus 1 over 512. This is going to be your answer. So the answer is you find the common denominator 512, no 512, yeah. And then you multiply 4, so that thing gonna be this number, and then plus 4, right? Oh, 5, 6, 64, and then minus 1. Yeah. It's just the calculation here. And then we compute it by hand. My God.
It will be like 4 something.
Yeah, so it's gonna be, okay. 2111. Yeah. This is how you approximate it for the square root 17 by using the Taylor polynomial. It is quite tedious with number, but your concept is okay, right? Because you just expand it in 2 terms for Taylor polynomial, and then you plug in the number you want.
So between this method and then there are another way to approximate the differential, which one is better?
Taylor polynomial is better because you can expand it to the terms you want. The one that you learn using differential or something like that, it's gonna be just a Taylor polynomial degree 1.
Okay.
Yeah. But the problem that we learned from this example is that if you ask 10 people to approximate the same thing, they could come up with different things, right? Because some people want to use degree 5, some people want to use degree 6, some people want to use center at 0, some people can use center at 1. So it's gonna be depends on what you pick. This is why when I write the exam, or when they ask you on the exam, we're gonna specify what center and what degree do you have to use, so everyone get the same answer. So be sure that you know how to do it when it is given that the degree is equal to something, the center equal to something, function equal to something. Now if you expand everything, expand it to infinity, it's gonna call Taylor series. We're gonna just expand Taylor polynomial to Taylor series. And I think we should do cos x and 1 over x here. Okay, cosine x. Example 5. Let fx is equal to cosine x. Can you find the Maclaurin series? Okay, Maclaurin series is the Taylor series, but you just have a center at 0. Find the Maclaurin series. Write out at least non-zero 3 terms, and then write the series in the summation notation. Okay, so first of all, we're gonna start from fx equal to cosine x. You differentiate 1 time, so you get differentiate cos, you get negative sine, right? And then you differentiate sine, you get cos. And then you get differentiate 1 more time, you get sine. Now after the 4th derivative, you're gonna get back to the cycle. So differentiate sine, you get cos. So it is in the loop now. And then now when you plug in, because you need the center at 0, this one Maclaurin series means center at 0. So you plug in f0, this is cos 0, which is 1. And then f prime 0, this is minus sine 0. This is actually 0. Right? And then f double prime 0. This is minus 1. You can see clearly that the derivative at the odd order, it's gonna be 0. And the derivative gonna be keep going in this way, right? And then the next one gonna be 1. So it's gonna be 1, 0, minus 1, 0, 1, 0, minus 1, 0, and keep going. This is how it's work for the Taylor polynomial for the cosine function. And now you can see that the term that have the coefficient 0 gonna be disappear for the Taylor series. So when you do the this is a Taylor polynomial already, so it's gonna be cosine x. Now it's gonna be the first term you have it, which is 1. The second term you don't have it because the coefficient is 0. The next term you have it because the coefficient is negative 1. and now it's gonna be negative 1 over, this is the second term, 2 factorial x minus 0 square, and then the next term you don't have it because the coefficient is 0, right? And then the next term it's gonna be 1, but now the degree gonna go to 4 now because this is degree 0, degree 1, degree 2, degree 3, degree 4. So it's gonna be x minus 4 to the 4th power, and then the next term gonna be 6, and keep going. Okay, can you write the cosine function here in terms of summation? So what it's gonna be? So it should be, of course, you can see that the sign gonna swap between plus and minus, plus and minus. You can see plus minus, plus minus, plus minus. So you can see negative 1 to the k should be in your series here. And then you can see that you have in the bottom you're gonna have 2, 4, 6. What should you do then? Can we do 2k factorial? And then k start from 0 to infinity. So k start from 0 to infinity. 2k factorial, the first term gonna be 0 factorial on the bottom, which is 1. The second term gonna be 2 factorial. The next term gonna be 4 factorial. And the next term gonna be 6 factorial. Okay, good. Sounds good. And then this is going to be x minus 0 to the 2k, right? Which is actually x to the 2k. This is the form of the Taylor series for cosine. Make sense? And after this point, once you make the Taylor series of cosine, we're gonna learn how to make the series of cosine 2x, cosine x squared, cosine x plus 1. You can do anything because you can just plug in. You're gonna get another series for cosine x plus 1, or you can do cosine root x because you can plug in here. So it's like a lot of things you can do about the Taylor series here, but the basic one is this is the cosine Taylor series. Okay, that you. So for sure, you're gonna need to learn how to guess the series in the summation notation, because this is what you can observe from the Taylor series and then transform it to the summation notation. All right, one more question on example 6 for Taylor series, and then we're gonna talk about the important series, and then we're gonna stop and take a look at the solution for exam 1. Because we have time left. So example 6, find Taylor series for fx equal to 1 over x center at x equal to 1. Okay. Fx equal to 1 over x. So this is actually it is x to the negative 1, right? When you differentiate one time, so you're gonna get negative 1 x to the negative 2. Well, and then you differentiate the second time, so you're gonna get negative 1 times negative 2 x to the negative 3. Right? You can keep going. The third time you're gonna get negative 1, negative 2, but now x to the negative 3, it's gonna go down to negative 3, x to the negative 4. You can do until you feel comfortable with the pattern. Now if you feel like, okay, we know the pattern already, you can stop. And then now you can say the center that they give you is 1, so you can compute at 1. So it is 1 to the minus 1, this is actually 1. And then f prime at 1, so this is actually minus 1, because you plug in x by 1, so this term gonna be 1 anyway. So it's gonna be f prime double prime at 1 here gonna be 2, and f triple prime 1 here gonna be -6. So you actually have all the numbers here, and then now you can guess the Taylor series. Now the Taylor series for fx equal to 1 over x around center x equal to 1 is, so now it's gonna be fx, which is 1 over x, equal to by the formula it's gonna be f1 plus f prime 1 x minus 1, and then plus f double prime 1 over 2 factorial x minus 1 square. So for today you can feel like this is super easy for some of you because it just plug in things. So hopefully you can memorize the formula now. It's just like this is the Taylor series, and then now f1 gonna be 1. This is going to be -1 x minus 1, and then this is actually 2 over 2 x minus 1 square, and then the next one is going to be 6 minus 6 over 6 x minus 1 cube. So once you cancel out, it's gonna be 1 minus x minus 1 plus x minus 1 square, and then minus x minus 1 cube, and so on. You can see that looks like the coefficient gonna cancel out perfectly, which is a case that you can claim it is true, because every time when you do it, you're gonna get number keep going. The next one, the fourth order derivative, you're gonna get 1, 2, 3, and 4, right? Which is gonna cancel with 4 factorial here. So at the end, this Taylor series for 1 over x should be this one. And when you write it in the form of the series, so you can say that this is actually summation -1 to the k x minus 1 to the k, right? Because k start from 0 to infinity. Because every time you have x minus 1 with you, and then the sign gonna swap between plus minus. Well, if it is start from minus, so you just change this one to k plus 1. That's all you need, you know. So -1 to the k means you start from plus, and then -1k plus 1, you can start, it's gonna start from minus. You just swap the sign over there. There's gonna be this type of question on the midterm one. So example 5 or 6 here. So make sure you study on it. It just memorize the formula of the Taylor polynomial, and then you show me how to do it in the summation notation. This is the easy part for chapter 9, using the Taylor polynomial to approximate function and doing the Taylor series. However, the next class, next week, we're gonna talk about power series, which is gonna be something a little bit harder compared to Taylor series. We're gonna wrap up today by looking at the important Taylor series. This is the one that people discover, and it's gonna be useful later. For 1 over 1 minus x, it's gonna be this one. Well, but I mean, if you have to use it, on the exam, it's gonna be given for you for that important Taylor series, because we're gonna use it later. But you can see that e to the x, you can expand it to this. Sine x, when you expand, you only have the negative, you only have the odd power. Cosine, you only have the even power here. Yeah, even arctan function, if you want to compute arctan easily, so you can do the series as well, Taylor series as well. Okay, then this is the important Taylor series that we're gonna carry to something next week, that we can do the power series. So next week Monday and Wednesday, we're gonna try to do the power series, which is we're gonna learn how to find the radius of convergence, interval of convergence, and also we're gonna learn how to tie it up with the Taylor series. Okay, the last 10 minutes for today, we're gonna just look at the solution for the exam because I already grade 6 questions, only the last page that I need to grade. But let's see. So many iPad here, so I cannot find mine. 1 second. I'm trying to airdrop, but okay. Found it. Why does it take so long? Did I do something wrong? Send already. Or is it possible to do it here?